Okay, so the next topic we're going to cover in the course is magnetism. So something a little bit different from what we've been doing recently, although there is a connection, as you will see a little bit later. Magnetism is in chapter 26 in the book, and there's a lot of content in chapter 26, and we're going to be covering some of it, but skipping over quite a bit of it. So we'll be covering a lot of the first four sections and very little of the of sections 5 and 6. In fact, I think we may not even be doing any of section 6, and definitely not doing section 7 on Ampere's law. Okay. So, and there will also be just a little short section at the end of this chapter of the lecture notes on electromagnetic waves. That actually comes from a different chapter, but we'll deal with that when we get there. Okay, so let's start with the obvious question. What do we mean by magnetism? We're all familiar with standard magnets, the magnets you stick on your fridge and that sort of thing. What's this whole phenomenon of magnetism all about? Well, the first thing I want to start with is the magnetic field. So there is something which is kind of like the electric field. We call it the magnetic field. And it's a field, it's a vector field, like the electric field, in the sense that over some region of space in which the field is present, there is a unique vector, in this case it's a magnetic field vector, associated with every point in space over that region of space where the field is present. Okay, so that'll become, if that sounds a little vague, it'll become hopefully a little clearer later through this lecture. Okay, the other thing to note is the magnetic field is associated with charges like the electric field. Of course, we know the electric field is caused by the presence of electric charge. That's true for magnetic fields as well. But the important thing about magnetic fields makes it a little bit different is that magnetic fields are really associated with the movement of electric charge. Okay, so charges will only feel a magnetic field when the charge is moving, and we're going to see later on that moving charges also create, as I say here, magnetic fields. Okay, so charges moving in a magnetic field feel the effect. How do they feel the effect? Through a magnetic force. And moving charges, as we'll see, also create magnetic fields. Now, the kind of magnetism you're most familiar with, for example, bar magnets, a piece of magnetized metal that will stick to your fridge, for example. This is a kind of magnetism known as ferromagnetism. So those are ferromagnetic materials. The origin of this type of magnetism is actually very complicated. Even though it's the more familiar kind of magnetism, it's kind of complicated. And if you're curious, you can take a look in section 7, but we're not actually going to cover that in the course. Okay, we're going to cover a simpler form of electromagnetism, simpler form of magnetism that does not involve this kind of ferromagnetism. Okay, so the magnetic field, you'll notice the symbol is B. It's a vector quantity, just like the electric field. You might have guessed it would be M for magnetic field, but it's not, it's B. And this new quantity, the SI unit for it is the Tesla, capital T. Okay, so what can we say about a magnetic field? Let's say there's a region of space over which we have a magnetic field B, and you have a charge Q, and the charge Q is moving with a velocity V. If you do experiments to measure the force which acts on that moving charge in the magnetic field, you will discover it is consistent with this equation here, equation 1. Okay, so we have the force due to a magnetic field, that's F sub B, is equal to the charge Q multiplied by, okay, now we have the two vectors here, V and B, and this is a cross product. Okay, I'll remind you what the properties of a cross product are in a moment. Okay, a cross product of two vectors, well, the one thing I can say now is it yields a quantity which is a vector quantity, right? And that's what we have over on the left side of equation 1. So what are the properties of a cross product? Well, one of them is, look, if you take the magnitude of the left and right-hand sides of this equation, okay, so you take the magnitude of Q, but what about the magnitude of the cross product? It's equal to the product of the magnitude of V, the magnitude of B, but also multiplied by this third factor, sine theta. And what's theta? It's the angle between V and B, illustrated over here in the figure. Okay, so if you have a vector V pointing in this direction and a vector B pointing in this direction, in the plane of this little square, this little shaded, gray shaded square, okay, then theta represents the angle between these two vectors. And here's how it works for a cross product, okay, indicated in this picture right here with the thumbs up. Here's how you determine the direction of the cross product of two vectors. You take the fingers of your right hand, so this is a right hand rule. Your right hand, you point them in the direction of the first vector, that's V, the first vector in the cross product, and you curl them in the direction of the second vector, B, and your thumb of your right hand points in the direction of the cross product. So that's illustrated again in figure A. Okay, so again, take your right hand, fingers of your right hand point in the direction of the first vector, curl them in the direction of the second vector, and you may have to twist or turn your hand in order to achieve that, but after you're able to do that, your thumb will be pointing in the direction of the cross product. Okay, so the cross product in this case is the force. Well, the cross product times the charge is the force, and because a cross product of two vectors points perpendicular to the original two vectors, that's an important point here. It means in this case the force will be pointing, the magnetic force will be pointing perpendicular to the magnetic field, perpendicular to the velocity. Okay, that's illustrated in the figure A. But because of equation 2, when the two vectors are parallel, well, they're parallel means theta is 0, sine of 0 is 0. It means you have a zero force when the charge is moving in the same direction as the magnetic field. That also applies, by the way, if the vectors are in the opposite direction. V is anti-parallel to the magnetic field. That would mean theta is 180 degrees. Sine of 180 is also 0. So when V is parallel or even anti-parallel to the magnetic field, zero force. When is the magnitude of the force a maximum? Whenever sine theta is a maximum. Sine theta is a maximum at 90 degrees. So that means the magnitude of this force will be a maximum for any given speed and magnetic field magnitude. The force will be a maximum when these two are perpendicular. Okay, so all of this is important to understand going forward. So let's take a look at some examples here. The first example, V is parallel to B. And what did we just say about that? Well, we said that the force is going to be 0 whenever the velocity and the magnetic field happen to be pointing in the same direction. Okay, what about this one? V is pointing up, so you have this positive charge moving upwards. The magnetic field points to the right. Okay, let's calculate the direction of the cross product together. So take your right hand, point the fingers of your right hand in the direction of V, and curl your fingers in the direction of the blue magnetic field vectors, which are pointing to the right. Okay, you're going to have to maybe turn your hand to be able to do this. And when you curl your fingers from the green vector to the blue vectors, you should find your thumb pointing into the page or into the screen. Okay, so there's another example. This example here, we have a positive charge moving to the right. And okay, what do these blue X's mean? Well, those are the magnetic field vectors, and the X's mean they're pointing into the plane of the screen. So do this same thing with your right hand, the right hand rule. Fingers of your right hand, point them in the direction of the green vector. Curl them in the direction of the blue vectors. Now those are pointing into the plane of the screen. Okay, so you curl them in the direction into the screen. You should find that your thumb of your right hand is pointing up. That's the direction of the magnetic force. Okay, great. Now what about this last example over here? The last example is a charge moving to the right, and the magnetic field is pointing into the plane of the screen. Well, isn't that the same as what we just did in the previous example? Almost. You'll notice that the sign of the charge is different. Okay, so the cross product of V cross B will still be pointing upwards, but the force will not be. Why? Because go back to equation 1. We're not just taking the cross product of V cross B. We're multiplying by the charge Q. If Q is positive, the direction is the same. But if Q is negative, then the direction changes. Okay? So it changes how it goes in the opposite direction. So the cross product will tell you the direction of the force if the moving charge is positive. But if the moving charge is negative, well, whatever direction you get using the right-hand rule for the cross product, you take the opposite direction for the force when the charge is negative. Okay? So that's why I say here, the sign of the charge affects the direction of the force. So at this point you may say, yeah, well, so what? What is it? Why do I care about forces acting on charges moving through magnetic fields? What does it do? What it does is this. If you have a positive charge moving upwards, as in the picture on the left, the magnetic field, these X's again are pointing into the plane of the screen. So you use the right-hand rule. It's a positive charge. Okay, remember that. You should find the force points to the left. So what happens is the particle feels the force, and if it's already moving upwards, it will tend to get deflected in the direction of the force. So it has the effect of deflecting the trajectories of charged particles. Same thing for the negative charge. The only difference, again, is that the force will be in the opposite direction as it would be for the positive charge. So that means the negative charge is deflected to the right. Okay, so what can we do with this? We're going to consider, we're going to look at charged particles in magnetic fields. And we're going to consider a uniform magnetic field. That just means the magnetic field is constant everywhere in the region of space where the magnetic field is present. Okay, so in this picture here, we have a magnetic field that is described by these blue crosses that are pointing into the page. So that means the magnetic field is pointing into the page. And what happens if we have a charge, let's for convenience make it a positive charge, and this positive charge is maybe at this point initially and it's moving in this direction? Well, the magnetic field creates a force, and that force causes circular motion.